So let's start our paper number 22. Sorry, paper number 21. The title of this paper is Modeling, Control, Design, Inclusion of Articulated Robots in Cyber-Physical Factories. So this means how we can control the motion, right? How we can mathematically model industrial articulated robots, and how we can include this robot in Industry 4.0 cyber-physical factory. So the main objective of this paper is to how we can mathematically model this articulated robot, and how we can control this, how we can control their motion, and how we can include this robot, this articulated robot, in a cyber-physical factory, Industry 4.0. First of all, what is this articulated robot? What is this articulated robot? So this articulated robot is basically looks like human hand. For example, Mitsubishi Melfa 4VR FLD, ABB Industrial Robot, KUKA Robot, Fanuc Robot, Universal Robot. So all these robots are articulated robots. That means the robot looks like the human hand. That is what is called an articulated robot. Every joint is having motor. Okay, so by controlling the motor, we can move this robot, and also we can move this end effector to the appropriate position. Every joint is having a motor. First of all, we need to prepare the mathematical model of this robot. In order to see the robot motion in our computer, right? Or in order to control the robot in our computer, we need the mathematical model, right? We need the mathematical model in our computer. So this paper is basically explaining two important models. One is called kinematic modeling, and the second one is called dynamic modeling. Kinematic modeling, two types: forward kinematics and inverse kinematics. Dynamic modeling, we will discuss this one by one. See, kinematic modeling means the robots joints and their corners, right, and their the location of the end effector. So the relationship between all these is what is called a kinematic modeling. Suppose if we give joint angles, it will calculate where the end effector will reach. So based on the joint angle, where this end effector will reach. Forward kinematics. So forward kinematics means from the angle to the end effector, right? So inverse kinematics means if you give the end effector, okay, based on that, calculate the angle. That is what is called the inverse kinematics. So for example, we have a conveyor belt, okay, and in order to pick and place a box from the conveyor belt, okay, the robotic gripper should reach a particular position, right? And also this joint should tilt some angle, right? So using this, we can calculate this. So forward kinematics and the inverse kinematics. Dynamic modeling means in dynamic model, we should consider the torque, mass, inertia, gravity, acceleration, etc. So dynamic model will include all these: torque, mass, inertia, gravity, acceleration, etc. So using the dynamic model, so mathematical model is classified into two categories, right? Kinematic modeling and as well as dynamic modeling. So using dynamic model, we can provide precise and accurate motion. Next is called motion. One is called a modeling, right? That is called a mathematical modeling, right? Okay, in order to control the robot in our computer, we need the mathematical model of the robot, right? So kinematic modeling and dynamic modeling. Then control design. What is control design? We need a controller, right? Because the robot should go from one location to another, right? So we need a proper controller. We need a proper controller so that the robot will reach in a correct position. That means the position, the speed, the trajectory. Okay, in order to follow this speed, position, trajectory, we need a proper controller, right? Conventional cascade control, right? What is conventional cascade control? Here we have multiple control loops working step by step. Position control loop, velocity control loop, current or torque control loop, etc. So position controller will decide the the speed, okay, and the velocity controller will provide the motor or torque or current, and inner current controller will directly control the motor. Normally, this type of method is used in industrial robots. Advanced motor-based control. Advanced motor-based control means controller will be directly using to the mathematical model. Through this, we can do gravity compensation, joint interaction, tracking error. We can move precisely and accurately. If the payload is changing, we will get a good response. The novel hierarchical control configuration. So this article is suggesting a new hierarchical control structure. So in this structure, they are dividing the control activities in multiple levels. Factory level control will decide the production task. Robot task planning. That means it will be like pick and place, like of jobs. Trajectory planning. That means it will find the suitable path. Joint control. Okay, each and every joint there is a specific position or speed, right? Motor control. This is to control the motor or torque. See, in this paper, they have used multiple software tools such as MATLAB, Simscape, then Robotics System Toolbox, RT Toolbox, Cirrus, Simulink. So the advantage of this is that before doing any real robotic operations, we can conduct test in a virtual environment. That is what is called. That is what is the use of different software tools. MATLAB, Simscape, Robotics System Toolbox. So MATLAB, Simscape is for simulation, mechanical, electrical, motor, robot simulation. Robotic System Toolbox. This is for kinematics, trajectory planning, robot algorithms. RT Toolbox, real-time control experiments. Cirrus for industry, robot, and factory simulation. Simulink, controller design and block-based simulation. So using these tools, we can conduct experiments. Before doing experiments in actual robot. Okay, so we can conduct multiple experiments in virtual environment. Then rapid prototyping of robot motion control. So rapid prototyping of robot motion control means developing the controller very quickly and do experiment in simulation as well as in a real robot. That is what is called rapid prototyping. First of all, we have to prepare the mathematical model. That means we need a mathematical model in our computer. We need a mathematical model in our computer, right? Okay. So after mathematical model, then design the controller. Okay. Once we have the mathematical model and then we have the controller, we can do the simulation. After that, we can tune the control parameters. Once everything is okay, then we can do then we can do what real-time hardware implementation. That means we can implement the same thing in a real robotic system. This will reduce development time, accidents, and also reduce the cost. See, what is the use of this in cyber physical factories? Our title is modeling. Yeah, modeling, then control design and inclusion. So modeling means mathematical modeling, right? Mathematical modeling, and to control this mathematical model, we need control, right? Okay, and then cyber physical factories. What is cyber physical factory? Cyber physical, as the name indicates, cyber physical. What is the meaning? Cyber physical means we have physical. Physical means we have real robots, we have real machines, we have real conveyors, we have real sensors, we have real PLCs, we have real computers, we have uh, uh, real physical thing. This is what is called a physical part, right? Then we have cyber part. Cyber part means the digital side, right? The software models, communication networks, everything is connected. And in cyber physical factory means everything is connected. Everything is connected. Okay. So now we are discussing about articulated robots, right? What do I mean by articulated robots? For example, in this case, the objective of this articulated robot is to pick and place the robot. Sorry, pick and place the object from the box. Okay, in this case, we have a box, right? So the main task of this articulated robot is to pick and place the part from this box into the CNC machine. Pick and place, machine loading and unloading, assembly, welding, inspection, packaging, palletizing, etc. For example, in this case, the conveyor belt. We have the conveyor belt and we have the box, right? So workpiece is coming through this conveyor belt, right? So we have RFID sensor, right? So the sensor will identify the box or the workpiece, right? Then that message will be communicated to the PLC, right? Okay, or the factory control system. Then after that, the robot will pick the object and then transfer this object into the next station. And all these informations will be communicated to the central system. Then Industry 4.0, right? So whatever topics we are discussing about robot, okay, we are discussing about the robot modeling, right? Robot modeling, control, then control design, simulation, everything. All these are directly related to Industry 4.0. Okay, so Industry 4.0 means smart manufacturing, cyber physical systems, industrial Internet of Things, digital twin, real-time monitoring, flexible automation, machine-to-machine communication, virtual commissioning. So digital twin, our main focus is digital twin, right? So we have the virtual model of the robot and we have the real robot, right? If we will be able to connect these two robots, the virtual robot and the physical robot, and there is a bidirectional communication between these two, then we can say this is a digital twin. So the main objective of this article is to, yeah, from the name itself, from the title itself, it's very clear. The first part is modeling, right? So prepare the mathematical model of articulated robot. Okay, that means again, this mathematical modeling is divided into two categories: kinematic modeling, dynamic modeling, right? So prepare the mathematical model of this articulated robot, right? And also we need a control. We need a control system, or we need a control to control this mathematical model. Mathematical model means in our computer, right? So we need so this part is very important, right? Okay, so checking the conventional cascade control or advanced model based control. So design it to control this mathematical model, right? And then conducting software simulation, right? Conducting software simulation and real-time experiments, and so that this system we can use in real Industry 4.0 cyber physical factory. So finally, I can say that this paper is very useful because after learning this article, after learning this paper, we will be able to understand how an industrial robot is working, right? How we can prepare the mathematical model, how we can prepare the mathematical model of an industrial robot, and then to control the mathematical model, we need a controller, we need a control design, right? So now we have our mathematical model and we have our control design, right? So we can simulate it, right? So simulation, real-time testing, factory integration is possible, right? So we can connect everything into the system: the robot, conveyor, PLCs, sensors, simulation software, communication system. So finally, it will be directly converted to a smart cyber physical production system. So that is the main objective of this paper. Okay, so we have the Ceros application, right? We have Mitsubishi Melfa robot, we have conveyors, PLCs, MES4, Robotino, digital twin. So this paper is directly related to the facilities, right? So utilizing the Ceros, okay? So utilizing the Ceros and prepare a virtual factory, right? And then after that, do a controller simulation. And then after that, do experiments in Melfa robot, right? So that is what is mentioning in this paper, right? Yeah. Let's see. So modeling, control design, and inclusion of articulated robots in cyber physical factories. This paper addresses the features and limits of the principles and means that provide and support the design of motion control for industrial stationary articulated robots and their involvement in cyber physical factories as part of the Industry 4.0 concept. The proposed methods are presented herein from the modeling of kinematics and dynamics. So modeling means mathematical modeling and as well as the dynamic modeling. Okay, considering ideal rigid bodies and principles of classical mechanics to their application in the design of so once the model is ready, next part is control, right? So conventional cascade control and advanced model-based control and use within commercial software tools. The paper demonstrates the modeling principles adapted for control design, where a specific novel hierarchical control configuration is outlined. There is an introduction of possible software such as Simscape, Robotic Systems Toolbox, RT Toolbox, Cirrus, and others. It includes the specific aim of the rapid prototyping of robot motion control, which is intended for user development and tuning. In conjunction with conveyor belts, robots manipulators are essential for cyber-physical factories built on the concept of Industry 4.0. The concept of Industry 4.0 is discussed in respect to the proposed algorithms and software means. So the keywords will be industrial robotics, real-time experiment, motion control, Industry 4.0. See, nowadays, okay, now we are discussing about articulated robots, right? So the mathematical modeling, control design, and the simulation and the real-time experimentation related to the articulated robots, right? Yes. So first of all, we should understand what is an articulated robot. So nowadays, in industries, uh, commonly using robot is what is called articulated robots. See, the main advantage of articulated robots is it will be looks like human hand. Okay, so like our human hand, right? So we can move our hand like this, right? So uh, so articulated robots is a type of robot looks like a human hand. That means it is having different joints, right, like this. So like a human hand, the robot can move. That is what is called articulated robots. That means this robotic hand, this robot can move in multiple directions. So this robot is used in multiple areas, right? So because of that, the control design is very important, right? So the control, because this type of robots are using in multiple areas, multiple fields. So its control is very important. Okay, regularly we have to check the control, right? Even though a minor mistake is not acceptable, right? So do a thorough research, even though the system is working, do a thorough research related to the control part is required. And through this research, we have to improve the performance of this robot, right? So because of that, we will be able to precisely control the motion of the robotic system of this articulated robot. See, one of the major problem was energy inputs. See, the energy consumption, right? Then the wear and tear of parts, production cost, motor heat, efficiency. So the main thing is that we need to convert the control algorithms, okay, more better, far and more better. So the main objective is to make sure that the control algorithms, the robot control algorithms. So that is the main objective. We need to improve. We need to improve the control algorithms. As I have already mentioned, what is a cyber physical factory, right? Cyber physical factory means we have real physical machines, and we have its virtual machines, right? Everything is connected, right? So in cyber physical systems, this articulated robot is a major part, right? And the machines, robots, conveyors, sensors, PLCs, computers, communication networks, simulation models, everything is connected. In cyber physical system and in digital twin, everything is connected, like our conveyor belts, the robot, the articulated robots, PLC, sensors, everything is connected. So is the main goal of the automation system, right? So we have sensors, right? Then from the sensor, we will get necessary information. So this information will send to the controller part or the PLC, right? Then from the PLC, output will be going to the robot, right? Then the operation will happen, right? That means production will happen, right? Then the controller will get the feedback or the production data. So the controller will receive informations from the sensor, right? And based on the information received from the sensor, the controller will act accordingly. Once and then the controller will give necessary information to the robotic system, and then the robot do his particular job, and then after that its data, its performance, then it will deliver data to the controller side. Then what are the jobs? What are the specific jobs this articulated robots is doing in industries? One is material handling, right? That means this articulated robot will pick and place different objects, and also this robot will take parts from the conveyor systems, conveyor belts, machine loading and unloading, packaging, palletizing. Then another one is called a welding, advanced automated manufacturing operation. So this type of articulated robot is using in welding operations, painting operations, machining operations, assembly operations. So this type of operations, this type of articulated, we can use this type of articulated robots in serial production as well as in mass production. You know what is the difference between serial production and mass production? So what is mass production? Mass production means, for example, one product. We have a one product, right? It will manufacture n number of times. That means, for example, this mobile phone, car, etc. So mass production. Serial production means, okay, we have a specific batch. Okay, once we will complete that particular batch, then production will stop. But mass production means large number of products will be produced. In serial production as well as in mass production, we can use this type of articulated robots. It will improve the production speed, repeatability, safety, precision, etc. Articulated robots belong to a class dominating today industrial production. Okay, 1,2. For this mass use, the control principles in control systems must continuously be subjects for testing, investigation, and improvement. This follows from a permanent effort to reduce a set of infinitesimal redundant energy inputs that lead to needless additional cost. The full robot integration into recent cyber-physical factories is a step on the way to the full robotization of production. Robots are used for handling as well as for automated manufacturing operations such as welding, painting, machining, or assembly in serial and mass production. An example of CPF. CPF means cyber-physical factory is shown in figure 1. See, this is the figure from a college, College of Polytechnic, Jihlava, and this was installed by Festo. This is an educational cyber physical factory from Festo. So Festo is the company manufactured this system. This is a cyber physical system actually. This is basically for educational purpose. That means industrial production operations. Students can learn this type of industrial production systems with the help of this cyber physical systems. This is like a small factory, and it is having industrial articulated robots, conveyor belts, sensors and actuators, PLC controllers, manufacturing and assembly stations, computer and communication network, production monitoring software, digital or virtual factory model. Everything is connected, right? So that we can simulate the smart factory operations. Background of analysis. See, we have a cyber physical factory, right? And then we have articulated robots, right? So this paper is discussing about this cyber physical factory plus this articulated robotic system. We can use this type of articulated robots for small applications to large industrial operations. There are so many case studies existed. The major common research areas was the coordination. The major research areas was the coordination between CPF different machines in CPF factories and different systems. So CPF factory means it is having so many machines with multiple systems, right? And that is one particular area. Okay, how this different machines and systems coordinate properly. Then the industry 4.0 ideas, how this industry 4.0 ideas will affect the business operations. Then the third one will be human robot collaboration, smart machines, manipulators, sensors, the collaboration between smart machines, manipulators, sensors. The production control based on digital twin. The future collaborative workplace will be like a smart production entities, right? So future factory will be future factories will be humans and robots will work collaboratively, right? So it will be like a collaborative workspace. That means in a smart production entities having different types of machines, robotic manipulators, mobile robots, sensors, actuators, intelligent controllers, etc. So as I have mentioned, the future will be a collaborative workspace. That means it will be a combined work between the human plus the robotic systems, right? So that means the human beings or the operator or the human beings will take the decisions, supervision, maintenance, etc. Whereas the some dangerous tasks or some repetitive tasks will be handled by this type of articulated robots. So like that, the future will be a collaborative. Workspace. But there are some challenges. Okay, some research challenges. First of all, I have already mentioned that in this paper they are mentioning the mathematical model, right? So this is very important. Okay, what is the current status of this modeling part? Is it exactly similar to the physical robot? That is the main question, because we need a mathematical model, right? Mathematical model means it represents the exact physical robotic system, right? Okay, so we have to, so still there are so many challenges. That means there is a gap. There is a gap between the mathematical model as well as the physical robotic system. So mathematical model means we will be preparing the robot based on theory, right? So when we prepare the robot based on the theory, we will consider links as rigid, and also in the joints we will be considered like no friction, and the measurements will be accurate, right? So these are our considerations. But in a real robotic system, of course there will be a friction, joint friction, right? Gear backlash, link flexibility, motor heating, sensor noise, payload variation, manufacturing tolerances, component wear, etc. So the thing is that we have a mathematical model, right? It should exactly match with the real physical robot. Okay, so in the theoretical model we have mass, inertia, friction, motor parameters. So it should be exactly matching with the operation of the real robotic system. That is one important challenge. That is one important challenge regarding the modeling side. So now the modeling part is ready. Okay, now the mathematical model is ready. Okay, just imagine we have our modeling part is ready. In order to control this mathematical model, we need our control system. We need control design, right? So we need advanced software tools. Okay, there are so many software tools available, right? So which software tool is suitable to run this mathematical model? So our main focus is to reduce the energy consumption, right? Okay. So the main focus is reduce the energy consumption, right? Whatever we are doing, the main focus is to reduce the energy consumption, right? We need advanced controllers. Okay. We need to develop the advanced controllers very quickly and also simulate. Okay. We need to tune it properly, testing properly. So which software is required? That is another research question. Which software is required? What are the software tools required? So in this paper, they are saying that hyper prototyping means quickly prepare the control algorithms, design simulation, tune the parameters, test this on the hardware, implement this in real robot, etc. So for that, we can use MATLAB or Simulink, Simscape, Robotics System Toolbox, Cirrus, real-time control toolboxes, etc. And the third one will be, okay, so the first part will be modeling, and the second one will be the control. So the first challenge was, what is the current status of the mathematical model? Is it exactly correct or not? So mathematical model means it should exactly represent the physical robot, right? So what is the current status? So this is a challenge actually. In order to control this mathematical model, we need a control. We need an advanced control system. So we have multiple softwares available in the market, right? So which software or which application is suitable to control this? And the third one will be now we have the cyber physical factory, right? Next is we are going to integrate this robot into the cyber physical factory. Okay, this robotic system is not a one-man show product, right? It should be an integrated part of a factory system, right? Okay, for example, in this case, what is this? In this case, what is the duty? The duty is to pick this part from the box and put the part into the CNC machine. Once the CNC machining is completed, the robot will go inside, then take it back. Okay, so it should communicate with our controller part, right? PLCs, conveyors, CNC machine, sensors, other robotic systems, MES, database, digital twin, production planning software, etc. So we have our control side, right? So the control side will decide, okay, what will be the job? What is the job of this particular robot? Okay, what time the robot should start this job? Okay, so in which location the robot should pick the workpiece, and uh, at what moment, at what time the robot should transfer this object into the CNC machine or into the next station. So the control part will decide all these things. If there is an error will happen, what will be the next step? So everything will be controlled by the control system. So there is so we have a mathematical model, right? Mathematical model means we have a virtual model, right? So we have a mathematical model, we have a control system to control this mathematical model, right? And then we have a real robotic system. So one is theory and another one is practical. So every time there is a gap. There is a gap between theory as well as the practical side. See, normally if you go to industries, they will be using different tools, right? But for theoretical research, we will be using different tools, right? So there is a huge gap. So there is a huge gap. There is a huge gap between this, okay, theoretical side as well as the practical side. So there are so many reasons because the resource availability is a major challenge, and there are some limitations between the development and testing. And small research groups are working separately. Consistently, there is no connection between the there is no connection between there is no connection between the software programmers and the control researchers. So the coordination gap is a major challenge. So we have software programmers, right? So we have software programmers or software developers, right? And then we have control researchers. So control researchers will prepare the mathematical algorithms. Okay. So this should be implemented in in the software side, in the commercial software. Okay. So normally there will be a gap. Similarly, the software programmers or software developers, they will develop tools, right? It should the control theories, they should not include this control theories. So there is a gap. There is a coordination gap. So this is the major problem regarding the practical implementation. See, coming to this paper, coming to this figure number 2. What is this? Coming to this figure number 2. See, this figure number 2 is showing the growth of robots. Every year, the use of articulated robots is increasing. The number of articulated robots is increasing. If you check, the use of this type of articulated robots in industries, the number is increasing every year. Even though there is a change in demand, raw materials, electricity, components, etc., input price, okay, there is a huge increase. Even though still the new robots are installing, commissioning, right? And automation is every day automation is increasing. Production flexibility, it will improve the production flexibility. It will reduce labor intensive operations. It will increase the quality and repeatability. So, new industrial software study about new industrial software tools is very, very important. Okay, just imagine we have our factories, right? In order to run the factory, we need the help of supplies, right? Just imagine we have a machine, sorry, we have a factory with we have different machines, right? And we have it's a cyber physical factory. That means everything is connected, right? We should connect this system with the suppliers, logistic systems, right? Because supplier is giving the raw materials, right? So supplier will update the availability of the raw material. Without the availability of raw material, how we can run this factory? So once the supplier will update the details of the raw material, the factory production planning system, for example, in our case, we have MES. So MES will update the system. Then we have our digital twin production schedule. So digital twin will simulate it, right? And from the digital twin, it will give information to the machines or robots. It will immediately start the production. So the real-time data. So the real-time data will be communicated to the digital twin. Necessary corrections will be happening. So in this way, we can collaborate with the production system plus as well as the supply chain. CPF, you already know what is CPF, right? I have already mentioned what is CPF. CPF means cyber physical factory. From the name itself, it's very clear, cyber physical. So physical, we have a physical space and we have a virtual or digital space. And these two systems are connected. This is what is called a cyber physical system or cyber physical factory. So if the physical system and the digital system is connected, it is called a cyber physical system. If it is related to a factory, then we call it a CPF, cyber physical factory. Okay. Otherwise, we will call it as CP system, cyber physical system. So you already know that we have a physical world, right? That consisting of sensors, actuators, robots, conveyors, machines, workpieces, etc. So in the cyber world, we have the control software, communication networks, internet, databases, simulation models, digital twins, monitoring systems, etc. So the main objective of this CPS or CPF is to prepare a communication interface between the physical world and the digital world. Now we are discussing about Industry 4.0, right? So you already know what is Industry 4.0, right? See, one of the main concept of Industry 4.0 is called a digital twin. What is this digital twin? It is the virtual representation of the entire physical factory. That is what is called a virtual visual. So we can visualize virtually the complete physical system. That means, for example, we have a factory, we have a real factory, right? Or we have a real robot, right? So preparing the digital representation of the real factory or the real robot. Because of that, we can simulate the real factory in our computer. Visualization. This is a major concept of Industry 4.0. If we have a physical system, the exact mathematical model or the exact virtual system we have, that is one of the main concepts related to Industry 4.0, visualization. The second one is communication. This is again another very important part of Industry 4.0. We have multiple things, right? We have robots, we have sensors, we have PLCs, machines, computers. So in this system, data is sharing between the systems, right, through networks, right, through communication interface, right. So that is the second important point, communication. So remember the points what I'm saying. Visualization, the second one is communication. Then the third one will be smart entities. Smart, what do you mean by smart? Smart means smart machines. That means machine will be able to understand their situation. So if I am able to understand, if this machine is able to understand this situation, the situation of this machine is what is called a smart. Okay, and also this machine will be able to transfer data from this to another machine, and also this machine will be able to take their own decisions. Then we will call this system will be a smart system, smart, intelligent. Okay, so these three are very important concepts related to Industry 4.0. Please remember the three terms what I have written here: visualization, communication. Visualization means the digital, the complete 3D representation of the entire factory in our computer. Then we have communication. Okay, we have multiple systems. Communication or data transferring between the systems is required. And the third one will be smart entities. The system, the machine will be able to understand what is my current situation. Okay, so the machine will be able to transfer data from one location to another, right? And also the machine can take appropriate decisions intelligently. There are several investigative perspectives from construction with a small application such as in 7.8 and case studies comparable with the industrial applications. The focus is concentrated on problems of system coordination in CPF and the influence of concepts of Industry 4.0 on business operations. The possible future trends are addressed towards collaborative workplaces combining human and smart production entities, machines, manipulators, sensors, etc. Unsolved research questions persist in the adjustment of derived ideal mathematical models and their parameters, which need to be in correspondence with the real-world robot features. Which tools are suitable for the hyper-prototyping of advanced control design that should reduce energy consumption in future applications, and how the robots are managed and integrated into sophisticated production procedures and systems represented by CPFs. This article analyzes specific applicable modeling software for improving model-based control design. The gap between theory and software tools used in practice is still large. This is due to the unavailability of theory sourcing and limited development and testing. It is determined by predominantly separated small working groups, divisions without regular interactions between software programmers and developers, experts and scholars deriving basic principles and practices. However, the number of robots grows continuously, as demonstrated in figure number 2. That is a constant commissioning of new robots into industrial production every year in spite of fluctuating demand and rising input prices. In this respect, analysis of newly available software tools for industrial use is important for study, including the investigation of mutual relations not only within one factory but connected suppliers using specific organizing systems and digital twins in combination with real systems in CPFs. The combination of physical and virtual spaces is referred as cyber physical systems or CPFs. And the aim of their commissioning is to create a communication interface between the digital and the physical worlds by integrating computation, networking, and physical assets. It is well understood that the interconnection between the physical world is represented by hardware, example sensors, actuators, robots, and cyber software. communication, networking, and internet. By using the concepts of Industry 4.0 as virtualization, communication, smart entities, there is an estimation of the specific possibility to reach a more efficient and optimal production flow. See, this figure is showing global industrial robot installations in 2021, then 2022 and 23, gray, red, and blue. This graph is showing the global industrial robot installations in three different colors: red, green, and blue. And in thousands, right? First one is automotive and transportation, then electronics and electrotechnics and electronics, then metal and engineering. So from this graph, we will be able to understand that in industries, the use of automation is gradually increasing. Automotive, transportation, electronic sector, industrial robots is commonly using. Because of labor shortage, quality, speed, repeatability, and safety, the robot usage is increasing. Another advantage of this type of robotic system is that based on the customer requirement, this robot can do flexible production. That is another advantage. That's why the use of the installation of robot is increasing every year. See, nowadays we are living in a new industrial environment, right? So why this? What is this new industrial environment? That means the production is basically considering customer, right? So the production will be a customer oriented production. So that is this new production era, right? So whatever be the production will be based on the customer. What is the requirement of the customer? Okay, so the company is producing a particular product. They will be basically considering only customer oriented production. That means customer oriented production means in our conventional days, one product is manufacturing in n number of times, right? But customer oriented production means based on the requirement of the customer, right? For example, if the customer is expecting, okay, so this much length, this much width, so customer A is expecting a product, and his interest is, okay, I need this much length, this much width. But customer B is expecting, okay, I need this much, I need this modification, this type of modification I need. So this is what is called a customer-oriented production. Customer-oriented production means what will be the output? We will get multiple product variants, right? So customer oriented production means, so the companies, majority of the companies, they are focusing customer oriented production. That means we know, we have multiple mobile phones, right? Multiple designs, multiple specifications, mobile phones we have. Why? Because they are focusing customer oriented. So customer oriented means we will get different varieties of products in the market. So nowadays the production will be completely based on customer oriented production. So please remember the key points, whatever I am explaining, please note all those points. Okay, what is customer oriented production? So customer oriented production means we will get different product variants in our market. Different mobile phones, right? If you go to Lulu, you can see Lulu shopping or avenues. You will see different types of mobile phones, right? Why? Because the companies they are manufacturing, their main focus is customer. So if they are focusing customer, then we will get different product varieties in our market. For example, nowadays if you go and you are ready to buy a car, you can choose what color is required, right? Engine type, interior design, seat material, you can choose automatic transmission or manual transmission, safety features, entertainment system, additional accessories. Of course, if you are going to buy a household consumer electronics, okay, different models, the size, the color, capacity, different functions, connectivity options, the user can select, right? So this is what is called customized or tailor-made or made-to-order product. That is what is called a customized, tailor-made or made-to-order product. In order to make this type of customized or tailor-made product, our production system should be not a rigid system. It should be what? It should be flexible, because we need to produce different variety of products, right? In order to make different varieties of products, right, our production system should be a flexible production system. Our production system should be a flexible production system, not only rigid, not a rigid system. Our system should be a flexible production system. Then only we will be able to manufacture different varieties of products. Otherwise, you will not be able to manufacture different varieties of products. So in order to make different varieties of products, our production system should be a flexible production system. What is the meaning of flexible? That means, so we have a production line, right? Using the same production line, we can manufacture different variants. See, if the customer order is changing, we need to change our production plan, raw material order, we need to change the robot task, we need to change the machine settings, delivery schedule. Okay, quickly we have to change everything. That's why I call it as we need a flexible production system. I hope you understand. Okay, so see, remember whatever key terms I am okay, just to remember the key terms. Okay, you will not be able to remember the complete paper, but whatever key terms I am mentioning, just remember all those key. Please note, or you can mark those key terms in your tablet. Okay. Okay, I have mentioned CPF. What is CPS? What is the difference between CPS and CPF? What is CPS? Cyber Physical System. What is CPF? Cyber Physical Factory. Okay, so we have a physical system and everything is connected. That is called a CPS. If it is related to a factory, then it is called a CP factory, Cyber Physical Factory. Then Industry 4.0 I have discussed, right? The mathematical modeling I have discussed. Articulated robots I have discussed. Control part I have discussed. Industry 4.0 I have discussed, right? Customized or customer, tailor-made, flexible, okay, I have discussed. So please remember all those key points in your mind. As I have mentioned, our so the production will be customer oriented production, right? In order to provide different varieties to the customer, our production should be a flexible production line, right? So that means if there is a change in the customer demand, okay, the system should be able to adapt to those situations, and the system will be able to produce that particular variety. Okay, so our production line should be flexible. Flexibility is required. Okay. Yeah, now our production line is flexible. Is that enough? No. Is that enough? No. We need raw materials, right? That means we need supply, raw material supply, component supply, transport and logistics services, production departments, warehouses, sellers and traders, customer service teams, right? For example, just imagine, okay, just imagine a simple example. If a customer needs a particular type of car, okay, having a specific color, okay, green, blue, or red, like that, okay. In order to produce that car, the supplier should provide the necessary raw material to the factory, right, on time, right? And then based on that, factory will start the production, assembly, inspection, storage, transport, and finally sell this car to the customer, right? So three things I have mentioned: supplier, our production line is, it's flexible, it is capable to satisfy the customer demand, right? Okay, we need supplier, service, seller tech. Industry 4.0 pilot production. What is called a pilot production? So now you understand flexible production and customer oriented, right? So pilot production means before starting the actual production, we have to do a small scale production. That is what is called a pilot. Industry 4.0 pilot production. Once the pilot production is successful, then only the same system will implement in a large scale factory. Okay, so before implementing this in a large scale factory, we will implement this in a small scale production system or small scale product. Okay, if it is successful, then we will enlarge this into a large scale production system. That is what is called Industry 4.0 pilot production. So I have discussed mathematical modeling, control, articulated robots, Industry 4.0, flexibility, customer oriented, right? Then pilot production. CP factory, okay, I have already mentioned what is CP factory, right? So there are two aspects. One is cyberspace, right? The cyber side means the digital side, control algorithms, monitoring systems, databases, simulation programs, right? Digital twin, computer optimization. The physical side will be the real factory, right? Production lines, conveyor belt, robotic system, sensors, actuators, handling equipment, etc. So we have physical and then we have cyber, right? So this is connected, okay, using industrial Ethernet, PLC communication, OPC UA, Profinet, sensors and data acquisition systems, MES, SCADA, IoT gateways. See, I have mentioned two important points, very important, two important points. One is called a mass production, and the second one is called a customer-oriented production, right? So what is the difference between mass production and customer-oriented production? What is the difference between mass production and customer-oriented production? So mass production means the same car is producing n number of times, no change. The same car, the same mobile phone, the same equipment is producing n number of times continuously, right? But customer-oriented production, that means the same standard product the company is producing, no change. The same standard product the company is producing. But customer-oriented production means the company is producing different varieties, different product varieties. Okay, that is the first point. Okay, remember what is the difference between traditional mass production and CPF based production. So the first point is in conventional mass production, the factory is making the same standard product, no change. The same car, the same mobile phone, the same equipment, the same vacuum cleaner, no change. But customer oriented means the company is producing different varieties. So the second point will be the production sequence will be fixed, no change. But customer oriented, the production sequence will be flexible. In order to produce different varieties, our production line should be flexible. Mass production is for big batch, but CPF, this is for small batch or single product. If we need to change, it will take too much time in mass production, right? But as I have already mentioned, CPF systems, they are ready to take the challenge or change. That means high level of flexibility. That means we can quickly reconfigure it. Offline planning is required in traditional mass production. Online planning and optimization in CPF based production. In traditional isolated machines, but in CPF, I have already mentioned, everything is connected, right? All the machines, all the robots, everything is connected. So this picture, see this picture. So this picture is obsolete concept of piece production made to order. So this means customer is giving an order, right? Then design the product, order the raw material, schedule machines and workers, manufacture the product, do the inspection, and deliver the product to the customer. That means for each order, they need to do separate planning. It will take too much production time. Cost will increase. Coordination will be difficult. There will be a delay in delivery. Automation will be very less. It will be very difficult to implement real-time changes. So that's why this is called obsolete concept. So in figure number 1, so this figure is showing different CPF modules. Okay, so different modules means every module is having a duty to do a specific manufacturing operations. Self-autonomous workplace, for example, inspection station, drilling module, pressing module, heating module, assembling module, revolving module, milling module, storage or magazine module. This is self-autonomous. I have already mentioned we have different modules. Self-autonomous. What is the self-autonomous? Self-autonomous means every module is having their own sensors, their own actuators, their own PLCs, their own control programs, their own inputs and outputs. That's why it is called a self-autonomous workplace. That means every module can work, individually. At the same time, it can receive command from the central factory system. For example, MES. So I have already mentioned in a CP factory, we have standard modules, right? So in order to connect these standard modules, we need standardized interfaces. And also necessary electrical power output is required because we have DC voltage is required, right? For the main station, we need power from the socket. That means 240 voltage, right? But for PLCs, HMI, we need DC voltage. Electrical power output is required. That means for PLC, sensors, motors, controllers, necessary power is required. Then we have, for example, stoppers, conveyors, right? So pneumatic power input is required. In order to operate, we need compressed air, right? So pneumatic power is required. So in order to communicate data, in order to share data, we need industrial Ethernet is required, modules, PLCs, computers, robots, monitoring system, etc. So because of the standard interfaces, we can connect, if we have 6 modules, we can connect all the modules because of the standardized interfaces. We can change the modules. We can add more stations. We can reconfigure new production line. Maintenance will be very easy. The role of PLC. Every module, I have mentioned what is a module, right? Every module, for example, we have 6 modules, right? Every module, every module is like uh, there is a PLC. There is a PLC connected with every module. What is the duty of the PLC? The duty of PLC is to receive information from the sensors signals, and then there is a control program already stored inside the PLC. So based on the control program, the PLC will give a necessary output to the robotic system. And based on that, motor, valve, cylinders, grippers will control. And then the operation status will send directly to the central system. And also, this PLC should communicate with the other PLCs also, other modules. It also will check the faults and the safety conditions. For example, in the pressing module, so for example, in the pressing module, sensor will check the status of the workpiece. Okay, PLC will stop the conveyor. Once the box is coming, okay. Once the box is coming, the sensor will check it. It will send a message to the PLC. Immediately, PLC will send a message to the actuator. Then the actuator will move up. Immediately, it will stop the box like that. So it will activate the pneumatic press. So sensor will confirm that pressing is completed. PLC will release the press. Again, conveyor will start the operation. So, so I have mentioned so many things. What is the difference between traditional mass production and customer-oriented production? Then cyber physical factory, digital twin, optimization, software, PLC, robot, machine, sensors, network, etc. Current modern industrial production is customer-oriented to offer customers a wide-scale portfolio of products with various properties and functions in different variants. It considers specific products such as vehicles, cars in automotive or consumer electronics for households, etc., which is customized according to customer wishes. That is, product is tailor-made. Such a requirement of the market leads to high demands on the organization and flexibility of the production, but also on the timing of forwarding services, suppliers, sellers, traders, as shown in figure. In this situation, Industry 4.0 was applied to pilot production that uses CPF as shown in figure 1. CPF, as was mentioned above, represents an approach that combines cyberspace, digital twins, computer optimization, programs, etc., with the physical world, consisting of real factories with production lines containing real machine tools, robots, and other production or manipulation machines and equipment. Both the cyber and real worlds are interconnected via specific envelope or interfaces that enable the producer to provide online managing and planning, thus changing and optimizing production. This makes it possible to move mass standardized unified production closer to a more customer-oriented one. The CPF representative depicted in figure 1 consists of several mutually compatible modules. These modules represent self-autonomous workplaces such as drilling, pressing, heating, assembling, revolving, milling, and storage magazine modules. They have standardized interfaces, electric and pneumatic power inputs, industrial Ethernet, and programmable logic controllers, serving as local control units such as configuration. Yeah, number 4. Okay. So next I'm going to discuss about I have already mentioned about the flexibility, right? So the main focus is nowadays the main focus of factory is to produce customer-oriented products, right? In order to make customer-oriented products, we need high level of flexibility. High level of flexibility is required in order to make customer-oriented products, right? In order to make different varieties, for example, in order to make different varieties of mobile phones, in order to produce different varieties of cars, a higher level of flexibility is required. So that is the difference between traditional mass production and customer-oriented production. In traditional mass production, the production sequence will be fixed, not change. But in customer-oriented production, higher level of flexibility will be there. So flexibility, production flexibility. So I'm talking about the term production flexibility. So we will be using different softwares. Okay, using software, we will discuss more about flexibility, production flexibility. RT Toolbox 3 version 2.00A Mitsubishi Xerox Studio 7 first. See, what is the use of RT Toolbox 3? RT Toolbox 3 is a software that is used to programming, simulation, monitoring, and commissioning of Mitsubishi industrial robots. RT Toolbox 3. So through this RT Toolbox 3, we can prepare the robot program, and we can simulate the robot models, check the trajectory of the robot. We can observe joint positions, collision possibilities, cycle time, etc. And also we can transfer the virtual robot program into real robot. We can transfer. Then that is RT Toolbox. That means RT Toolbox 3 means we can program the robot, the articulated robot, prepare the program, simulate everything. Xerox Studio. Xerox Studio means we can simulate a complete virtual factory with the help of Xerox Studio. Now this is 7. Now we are using Xerox 6. We can simulate a complete virtual factory using this Xerox Studio. Robots, conveyors, CNC machines, sensors, PLCs, storage stations, etc. That means we can virtually create a production line. Okay, we can test robot and PLC programs. Material flow we can check. We can check different production sequences, virtual commissioning. We can reconfigure production system. So I'm discussing about the production flexibility using software. So production flexibility using software, right? So that means we can using this software, we can simulate different scenarios, right? So that will give you a higher level of flexibility because the main focus is customer oriented production, right? So what is customer oriented production? Customer oriented production means the main focus is to produce different varieties. To produce different varieties, we need a higher level of flexibility. A higher level of flexibility is required in order to produce different varieties. So to get a higher level of flexibility, we can use this type of softwares. So you can virtually create different scenarios, conduct different experiments. You can create different scenarios. So this software will give you a higher level of flexibility for what? Customer-oriented production. Understand? Yeah. See, next we will be discussing different sections. Section 3 is mentioning about the robot topology. Okay, so section 3 is mentioning about the robot topology. Section 4 is for mathematical model synthesis. Section 5, conventional cascade control, that is related to the control part, advanced model predictive control. Then 6 to 7, simulation. What are the software tools used in real robot motion control? Section 8, the integration of this robot into a CPF, intelligent CPF system. And finally, conclusion. So the title is, modeling, then control, right? So control, two concepts: conventional cascade control configuration, advanced model predictive control procedures. Yeah. See, robot topology. So in this paper, they are mentioning about Mitsubishi RV4 FLD. This is a stationary industrial articulated robot. I will zoom this. Yeah. Yeah, this one. This is a stationary industrial articulated robot. Okay, this is installed in a cyber physical factory assembly module, right? Okay. So this robot is used for mathematical model synthesis, computer simulation, control design testing, real robot experiment, CPF integration. What do you mean by robot topology? Robot topology means the structure, the mechanical structure of the robot. How many links are there? How many joints? How many joints? How joints are connected? Okay. So what about the rotation of the axis? Then tool center, etc. So the main job of this robot is to, this is called a Mitsubishi 4V4 FLD, Mitsubishi RV4 FLD. The main job of this robot is to pick and place the components, change the position, assembly, etc. The robot is having 6 degrees of freedom. This robot is having 6 degrees of freedom. That means 6 independent joint movements. We can control 6 independent joint movements: Q1, Q2, Q3, Q4, Q5, and Q6. So normally, so Q1 will be base. We can tilt this base to right side or left side. Then Q2, it will tilt this forward or backward. Then elbow. Then forearm tool assembly. Then wrist will bend. Then flange. That is called a Q6. So this 6 joint movements will be there. So regarding the mechanical components, the robot is having a base to the flange, having 6 arms or legs: base, shoulder, upper arm, elbow block, forearm, wrist with the flange. So flange means here you can connect gripper, welding gun, painting tool, drilling tool, etc. That means this is the last mechanical interface where we can connect the end effector. TCP means tool center point. So the reference point where the operation is happening is what is called a tool center point. For example, this is for welding operation. Okay, so the welding tip point will be the tool center point. Okay, if you use gripper, okay, then this gripping point will be the TCP. Then drilling, if this robot is used for drilling operation, then the drill bit tip will be the TCP, tool center point. Okay, then painting gun, the spray reference point will be the TCP. So when we program this robot, basically we will be considering the TCP, tool center point. The tool center position will be based on 3 Cartesian coordinate system. Okay, you know Cartesian coordinate system, X, Y, Z, right? Okay, X, Y, Z, right? Tool orientation is required. So the complete pose of TCP will be X, Y, Z, and A, Z, B, Y, and Z, Z. We have 2 coordinates. One is Cartesian coordinates and the second one is joint coordinates, right? That means we can use user TCP and then joint control. Then coming to the mathematical model analysis, model synthesis. Now we are going to simulate this, right? So before doing the simulation, we need the mathematical model, right? We need the mathematical model plus we need the control. How we are going to prepare the mathematical model? There are 2 different mathematical models. One is kinematic model and the second one is called dynamic model. Initially, the robot links will be considered as ideal rigid bodies. That means the robot arms will not bend or do not change the shape. So kinematic model means force, torque is not considering, only considering the position, orientation, velocity. The relationship between position, orientation, velocity is called a kinematic model. Forward kinematics. Forward kinematics means once it should know the joint coordinates, it will find the TCP's position and orientation. Inverse kinematic means if we give the TCP position and orientation, it will find the joint coordinates. So dynamic means the robot is moving. Okay, dynamic means the robot is moving. That means the force, torque, mass, inertia, gravity, etc. Everything. Okay, so this is the general dynamic equation. Again, forward dynamics and the inverse dynamics, similar to the forward kinematics and the inverse kinematics. Mathematical model. Yeah. Think about kinematics model and the dynamics model. So kinematic model is used if the robot joint is shifting where the TCP will reach. Here we are not considering torque, mass, force, etc. Only this position and orientation is considering. That is called a kinematic model. Only the position and orientation is considering. In order to make this model, Danavitt-Hartenberg method is using. Danavitt-Hartenberg, DH method. So what is this Danavitt-Hartenberg method? For example, if there is a robot having two joints, okay. So this is a method to represent the geometric relationship between two links, nearby two links, called a DH method. So every robot joint is having a coordinate frame. Then from this frame, what will be the next frame? Rotation, translation, link, length, link twist, etc. Using a 4x4 homogeneous transformation matrix. If you multiply all the joint transformation matrices, you will get the position and orientation of the TCP. For example, joined, so this, I will zoom it. Yeah, so this is the joint. So okay, this is the joint data, right? Q. Okay. So the robot is having six joints, right? Okay, so this Q1 is base rotation, Q2 shoulder rotation, Q3 elbow rotation. So T represents the transpose. Then operational coordinate vector Y. So this is representing the position and orientation of the TCP, tool center point. XYZ means the Cartesian position of TCP. AX, BY, and CZ. AX means the orientation about x-axis, BY means the orientation about y-axis, CZ means the orientation about z-axis. So the complete pose of TCP will be based on the three position coordinates and the three orientation coordinates. And forward and inverse kinematics. So we have mentioned a DH model, right? Okay, once this joint values will know, based on this, the position and orientation will find. That is called forward kinematics. Inverse kinematics means if we give the position and orientation, it will find the joint values. For example, if the user is giving an instruction to take a particular object from a component, right? Okay, so now I'm giving the TCP point, right? So using the inverse kinematics, it will automatically calculate the joint, the moment of the joint. That is called the inverse kinematics. So in the forward problem, so this robot is a 6 degree of freedom robot, right? Okay. So forward problem means having three linear translation x, y, z, and three rotations. So x-axis rotation, y-axis rotation, and z-axis rotation. Okay, so this will be included in a transformation matrix. So base, shoulder, upper arm, elbow, forearm, wrist, flange, TCP. Okay, multiply the transformations, we will get the final pose of the TCP. So do not change the order of the multiplication. So T1, T2, okay, not equal to T2, T1. So we should follow the correct sequence. So DH parameter, what is this DH? We already discussed Denavit-Hartenberg DH concept, right? So every joint or link we can define using every joint or link we can define using the DH parameter. So QI, DI, AI, alpha I. QI, DI, AI, and alpha I. QI will be the rotation based on the previous frame. Then link offset, translation distance. Then link length, link twist. So this is the DH transformation matrix. From one frame to the next frame. This is the transformation matrix. So the simple working will be the robot controller will receive the joint values Q1 to Q6, but every joint produce this matrix, DH matrix. Okay, then multiply this matrix from base to the flange, or from base to gripper, multiply it, so that the gripper or TCP will get this position. And then controller will check whether the TCP box position is correct or not. So this matrix is very important. See, this figure is showing Mitsubishi RV4FLD robot kinematic analysis. This is showing the two-dimensional view. So here we can see 0 to 6, right? 0, 1, 2, 3, 4, 5, 6. This represents robot bodies or limbs. Zero to 1, yeah, like that, yeah. Zero will be the base, right? Then 1 will be the shoulder-related body, then upper arm, 2, then 3 elbow section, then 3 dash, fixed right angle elbow section, forearm, wrist, flange, tool section. So this 5 is mainly for inverse kinematics. I have mentioned the transformation metrics, right? So every transformation matrix is having DH parameters, QI, DI, AI, alpha I. Some will be variable, some will be related to the robot manufacturing constants. QI will be the rotation angle, DI join the offset through the joint axis, AI will be the link length, alpha I means the twist angle between the nearby joint axis. So in this robot is having 6 degrees of freedom. These are the joint variables. Fixed geometric parameters such as H0, H1, then L2, R3, L3, L4, L5, etc., L9, that represents the height, length, elbow, etc. Okay, this will be fixed. Okay, fixed geometric parameters. This will not change. This H1, this is fixed. This will not change. See, next is inverse. Inverse kinematics means the required position and orientation, TCP, is given. Based on that, joint angles will find. Numerical, two methods. One is called a numerical solution. Numerical solution means using, Newton-Raphson method, Jacobian inverse, Jacobian pseudo inverse, numerical optimization, etc. It will take too much calculation time. Analytical solution. Analytical solution using, triangles, distances, angles, etc. Okay, from this you can see this using this triangle, geometric relationships. So two methods. One is numerical solution and the second one is called analytical solution. So analytical solution will be, we can easily calculate, quickly calculate. Very suitable, very much suitable for real-time control. So there is a point E, right? So this is called the elbow reference point. This is for conducting the geometric analysis. So this is a reference point to conduct the geometric analysis. Then base joint angle Q1. Q1 is equal to A tan 2 YE XE. Then vertical height difference is F. Horizontal radial distance, effective length, shoulder to target distance, triangle length, triangle angle, target, elbow angle, calculation sequence. So the calculation sequence will be the target reference point E, then after that Q1, then H, F, G, E, C, V, omega. Okay, so after that, Q1, Q2, Q3, Q4, Q5, 6, 6, then finally calculating the TCP orientation. First of all, we need to find the reference point of E. The endpoint reference will be F flange point, TUVP. Transformation chain, AX, BY, Z, Z. Orientation. Then robot dynamics model. Dynamic model will consider the moment of inertia, joint velocities, effect, motor torque, etc. Lagrange equations of the second type. So in order to do the robot dynamics, second type Lagrange equation is using. Here V represents the kinetic energy and P represents the potential energy, and L represents kinetic energy minus potential energy. If you simplify the Lagrange equation, you will get the standard equation of motion of robot. This one, MQ, this one. So the mathematical side we have discussed. Next is the control concepts and principles. Non-model based conventional control and model based advanced control. The first one will be PID based cascade control, commonly using in industries. The second one will be robot mathematical model predictive control. So the conventional PID control is actually already proven technology. Simple structure, easy implementation, less computational requirement, reliable operation, PID parameters we can tune. Every joint, we can give specific controller. The second control approach will be the model-based predictive strategy. Using the kinematic or dynamic model, we can predict the future response. Even though the controller is how much advanced, if the reference trajectory is not properly designed, the robot motion is not correct. Conventional cascade control. Continuous and discrete PID proportional integral derivative. It is the integration of these three: PID, proportional, integral, and derivative. So where UT is the output, UT is the controller output, and ET means the error. ET means the error between the reference and the measured output. KP means the proportional gain. TI integral time, TD derivative time, ET error. Then proportional action. Based on the existing error, controller will give the correction. So we need software tools to analyze the robot behavior and also design the controller. We need suitable software tools. Using this, we can prepare a detailed robot model, and also we can verify the kinematics. We can simulate the dynamics, plan the trajectory. We can test our controller, identify the collision, conduct a real robot run, acquire robot data physically. We can compare the simulation as well as the experiments. The role of CAD tools, NX Autodesk Inventor, that will give you the accurate 3D geometry of the software of the robot. From the CAD model, we can find the parameters such as link length, masses, center of gravity, moments of inertia, axis offset, body geometry, collision envelopes. These parameters are very much helpful for the dynamic model accuracy. Center of gravity, moment of inertia. See, CAD model is actually a realistic ideal model. It will be different from the real robots, cables, gearbox friction. It looks like a realistic ideal model. Okay, another one is called a Simscape multi-body MathWork. Multi-body modeling library. So using the CAD model, we can conduct the dynamic simulation. Okay, import the CAD model in Simscape, define the mechanical joints, use the link, masses, and inertia, simulate the gravity effects, connect motors or actuators, visualize the joint motion, test and connect controller, and verify the dynamic behavior. During the development of the initial stage of robot development, 3D CAD model will be available, but dynamic equations is not available. No physical prototype. So in this case, we can use the Simscape multi-body CAD model. We can convert this into executable physical model. So before manufacturing the prototype, we can simulate the robot. This is called rapid drive prototyping. So this figure 8 is showing the Simscape multi-body blocks. The robot model is showing in Simscape multi-body. Solid, revolute, joint, rigid transform, world frame, mechanism configuration, joint actuator, joint sensor, and a solver configuration. Mechanics Explorer will give you the visualization of 3D simulation. Through this, we can see the robot configuration, joint movements, link orientations, TCP motion, imported CAD geometry, mechanical animation, and reference coordinate frames. We can import the robot from NX or Inventor. We can keep the physical parameters itself. Another software is called Robotic System Toolbox, MathWorks, MATLAB, from MATLAB. This is for modeling, planning, simulation, etc. So Simscape will give you the simulation. The Robotic System Toolbox will give you the structure creation, forward kinematics, inverse kinematics, geometric transformations, Jacobian calculations, trajectory planning, dynamic calculations, collision checking, motion visualization, controller development, simulation data analysis. Every body is having a parent body, joint type, joint axis. Next page. Yeah. So this is the MATLAB structure having a parent body, joint type, joint axis, fixed transform, mass, center of mass, inertia, collision geometry, etc. So this figure 10 is showing the robot structure. And figure 11 is showing the MATLAB command window. So the physical parameters such as arm length, link masses, moments of inertia, center of gravity, joint axis, geometrical envelopes, collision bodies. So kinematic verification. So we have our DH transformation we discussed in section 4.1. We can verify using the MATLAB functions. So figure 12 is showing the robot simulation animation, the TCP trajectory, join motion, collision envelopes, wireframe points, desired and actual robot positions. So we can check different signals in simulation, join space, TCP position, TCP orientation, dynamic quantities. So we have Simscape and robotic system toolbox. So we can import the model from the CAD software. Then we can simulate this in Simscape multi-body simulation. Plus, we can, using the robotic system toolbox, kinematics, planning, and collision test. After that, design controller, simulation verification, real robot experiment, and data acquisition. RT Toolbox 3. This is the engineering software only for this Mitsubishi robot. We can prepare the program. We can do the 3D robot simulation, check the join motion, visualize the TCP trajectory, communicate with the robot controller, debug the program, operate the real robot, record experimental data, do the simulation into real robot motion. This is called Cirrus Studio. This is a factory simulation software. Majority of the capabilities will be related to the RT toolbox. Here we can completely simulate a factory model. Also, we can simulate 3D robots, programming the robot, motion simulation, trajectory verification, program debugging, sensor actuator simulation, PLC communication, industrial interface integration, real robot connection, virtual commissioning, production system simulation. In Cirrus Studio, not only a single robot, we can simulate everything: conveyor, storage, machining, assembly, sensors, PLC, etc. So the complete cyber physical factory we can model in this Cirrus. We can prepare the digital model of everything. That means before operating the real systems, we can completely operate the factory virtually. So through that, we can reduce the risk of collision. We can identify programming errors, robot reach, cycle time, production sequence, etc. Integration of Python. Using Python program, we can generate robot commands, simulation parameters, process input output data, calculate the trajectory points, automate repeated test, save measurement data, optimization algorithms, external digital systems, communicate with external digital systems. So this figure is showing the Mitsubishi RV4 FLD robot in a virtual environment. Using this, we can visualize the robot. RT Toolbox 3 is only for this Mitsubishi specific environment, but Cirrus Studio means multi-vendor. It's a factory-oriented environment. RT Toolbox means it is only for the robotic programming and simulation. But Cirrus Studio is for a robot as well as the complete factory simulation. See, robot modeling is not only a single procedure. Okay, it consisting of mathematical kinematic modeling, dynamic modeling, 3D CAD modeling, robot body parameter identification, trajectory planning, path interpolation, time, parameterization, controller design, simulation, physical measurements. Time history, how a physical quantity is changing as time is changing. That graph is called time history. Simulation. Using G code. G code is basically used in CNC machines, right? And it is used in robot trajectory also. This is showing the G code. That means the motion of the robot. This one is showing the Melfa language programming. Melfa language is for the robot, Mitsubishi robot. For example, servo on. Servo on means to enable the servo like that. Then PR1, PR2, these are reference points. Okay, so P1, P2, P3, P4, P5, like that. So different points. So this is the real figure number 18 is showing the real robot feedback results. Every graph is showing J1, J2, J3, J4, J5, and J6. Eighteen C is showing the current feedback. So finally, this coming to the conclusion. So this paper is basically explaining the mathematical modeling of Mitsubishi RV4 FLD robot. Okay, once prepare the mathematical model, next one will be the control part. Okay, then the motion control. Then for that we need different types of softwares. Then do some simulations in the software. After that, real experimentation, and finally Industry 4.0 integration. So this workflow is mentioning in this paper.